In this lesson, we are going to learn how to calculate standard formation of a few things. First of all, we are going to look for the standard formation of entropy, and then we have enthalpy, and then we have Gibbs Free Energy. And notice how the term standard is represented by that superscript, okay? Superscript of look like a circle or a letter O. Now the word standard represented by this superscript letter O is not referring to the STP standard temperature pressure that we are dealing with when we're working with the gas law, where we have 0 Celsius and pressure 1 atm. The only difference that this standard from this STP is that look at the temperature. It's not at 0 Celsius, but it is rather at 25 degrees Celsius. That is a very comfortable temperature. Where STP right here, this is referring to the 0 degrees Celsius. That's freezing. That's pretty cold. But the pressure is the same thing, 1 atm. And when we talk about solution, we're talking about 1 molar or 1 molarity of that solution. So let's look at the equation as a whole and how are they relate to each other. Notice how they all have the same or very much similar format. We can call it the same format. That is, it's always relative to this right here, delta. What is delta again? Remember, delta is changes, right? So what does changes mean? Well, in chemical reaction wise, changes always refer to product minus reactant. Or we can think of final minus initial. So all of them are looking for the changes in terms of delta S, delta H, and delta G. And look at the little circle on top, that superscript that tells you are calculating at standards. In this case, standard entropy, standard enthalpy, and standard free Gibbs energy. And the equation is pretty much the same thing. You take the sum of the product minus the sum of reactant for all of them, except for one thing that's different, is that for delta H and delta G, for any element, most likely like pure elements, for instance, let's say I have sodium as a metal form, we would know that the delta H formation for Na would be 0, or O2 would be 0, or something as simple as, how about hydrogen is a common one, okay? So notice that would tell us that those delta G or delta H formation, those would be equal to 0. And sometimes they are not given to us, we have to know that's equal to 0. But before we try to solve one of this problem, we need to realize how it is related to the whole entire thing, specifically to heat. Well, first of all, heat is represented by Q, right? And we learned that Q equal to heat and is also equal to delta H, which is the enthalpy, which is the content in the system. And delta H means the changes in the content system. So heat is a transfer of energy, which is equal to the changes in the energy in the system. Now we also learned a negative Q, that means we are losing or the system is releasing heat. So we can make a relationship, hey, if I have negative Q or negative heat, therefore I must have negative delta H. So negative delta H and negative Q, releasing heat. And we know that the word releasing heat or releasing energy, that is also referring to the exothermic reaction. Now exothermic, this right here is heat, okay, or energy. Exo means exit. So you exiting the heat reaction, so you are releasing. So right away, when I give you exothermic reaction, you have to know that it is negative delta H and negative Q. Let's look at the opposite, where we have positive Q. We will, of course, let's look at the opposite when we have positive Q, and positive Q equal to positive delta H. And instead of releasing heat in terms of exothermic, we have endothermics, okay? Endo is for enter, so the heat is enters the system or chemical reaction. So endothermics. When you see endothermics, you will know right away is positive delta H and positive Q. Well, in this case, we have the delta G naught. What does that tell you? So we can actually relate that to the delta G naught if we have positive delta G naught, okay? Or standard changes in G. If we have positive delta G naught, that tells you, just like in electrochemistry, it is a non-spontaneous reaction. Where if we have a negative delta G naught, okay, when we have negative delta G naught, okay, this tells you that the reaction is spontaneous. So by looking at the changes in G, we know if the reaction is spontaneous or not spontaneous. So let's solve one problem together. I'm going to solve for delta H, delta S, and delta G. Okay, so let's start over here. So let's look for delta H naught, standard formation. And of course they give us a table where we have to realize that look at the table, we have the unit for each of those specific thing. And look how we have the negative. That tells you that we have kJ or kilojoule over mole. So let's try this problem. Again, there's a mistake right here. This is supposed to be joule rather than kilojoule. Okay? Let's go back to the equation again. It's the sum of product minus the sum of reactant for all of them, except for any element in any pure element for delta H and delta G formation would be 0. So let's just work this problem together. It's always product minus reactant. So we look at this reaction here. Here's the product, and this is relative to the reactant. So keep that in mind, okay? And notice how we have the letter N and M. What does that tell you? Those are the coefficient. Those are the number of mole, okay? Because the number of mole will affect the total as well. So for delta H, let's look at the product. We have 2 mole of this compound here. So I can say that I have 2 mole of that compound. What is the values for delta H formation? Which is negative 1134.70. There you go. And now, that's all I have for the product. And that product is going to subtract the reactant, just like we have here, product minus reactant. So I put the bracket within the bracket at parentheses, okay? So in this case, we have 4 of Cr, and I know right away this must be equal to 0, because it's an element. Okay, so it tells you the table is 0, and sometimes it's not given to you. So here we have 4 times 0, and then we also have 3 oxygen. Oh look, that's an element form, and it's all equal to 0 as well. And look at that, we have oxygen right there, which is an element. So we have 0 again, even look out. And then we have oxygen. Notice how it is an element, right? It is a pure element, so it is 0. So again, even the table gives us it's equal to 0. So even without looking at the table, we need to realize these are 2 or 0 because they are pure elements. So we have 3 times 0. So we can kind of, hey, I can say that right there, 0 times 4, 0 and 3, and we add them all together. Of course, this whole thing will cancel out equal to 0. So our final answer is pretty much just this part, right? And anything minus equal to 0 will equal to so. So in this case, I just plug into the calculator. 2 times negative 1134.70. And then we get our answer equal to negative 2.26940. And what's the unit for it? It is kilojoule over mole. That's for delta H. And what does that tell you? Negative delta H. That tells you we have a negative Q, which in this case is an exothermic reaction, or we are releasing heat. Now let's solve for delta S naught. The same thing is that, and we're doing the same thing. We take the sum of the product minus the sum of the reactant. In this case, the product for the values of this compound, again, it is 2 times, and for the delta S formation, in this case, is, okay, how we have 2 mole, okay, minus the reactant, which in this case, remember the exception again? only delta H and delta G, where we have 0 for any element, but S is not. So we have to realize there is a values for it. So in this case, we have 4 times CR. CR is 23.77. And notice how it's the sum of reactants, so we need to add them together, which in this case we have 3 oxygen. Since the value for oxygen is 205.138. There you go. Isn't that easy? Now I just plug into the calculator. And notice how I have the caret symbol, right? When you see that, you just assume that is a parenthesis there. So 2 parenthesis 81.2 parenthesis minus parenthesis 4, okay, 23.77 parenthesis plus 3 parenthesis 20 or 205.138 parenthesis. And there you go. We have a final answer equal to negative 548.094. Isn't that easy? And what's the unit for it? Of course, is joule over mole times Kelvin. So that's the beauty of using parentheses. We don't have to simplify it individually. We just plug in directly into the calculator. Then what about delta G? So delta G naught, okay? And in this case, delta G naught, well, we have the same thing as product minus reactant. So we know the product is that one, and it is 2 of that, and that is negative 1053.11, okay? And caret symbol to group, that is this reactant, minus the sum of the reactant. So we have 4 times chromium. Notice how this is an element. I know right away it is 0. And we can prove that right there. See right there, 0. And then we also have oxygen, which I know right away is 0 because it's an element. Okay, so we know 0. So this can simplify equal to 0. And our answer just be that part only, which we know I can put parentheses, 2 times parentheses, negative 1053.11 parentheses, and still that will give us answer, which is negative 2106.22. And what's the unit? Kilojoule over mole. And what does negative delta Q represent? It is a spontaneous reaction. Isn't that beautiful? So this right here tell you that is spontaneous, where this right here tell you it is an exothermic reaction. Okay, so notice how the values tell us something about the chemical reaction. Isn't that beautiful? Here we have a very common one, right? The combustion of methane. Very explosive and very beautiful. So here we have this, of course, larger table, but the same concept. And of course I make the same mistakes. That is supposed to be in joules, okay? So this one is joule over mole times Kelvin. Here, of course, we have kilojoule over mole. And here we have kilojoule over mole again for the delta G. So let's look at this problem together. Let's solve for delta H again. Okay, so delta H is standard formation. Notice how this is formation of that substance, but this is the delta H of the whole entire reaction. So what we have again is the sum of the product. Here we have carbon dioxide and water, and we have that is 1 right there, 1 mole carbon dioxide because there's no coefficient. So what's the values for CO2? CO2 is right here, negative 393. Negative 393.5, okay? And we're gonna add to 2 moles of water. So plus 2 right there. And what's the value for water? Negative 285.8, okay? And that's it for the product. So we now close it with a bracket. Then we minus to the reactant. In this case, CH4 right there, okay? How many do we have? 1. So we put 1 right there, CH4, negative 74.8. A1, and we plus 2 moles of oxygen. I know this is oxygen is an element, so it's got to be 0. And I can prove that to you right there. Look at that. Isn't that beautiful? So we kind of ignore that part. Now let's plug into the calculator. So again, every time you see the caret, just put parentheses. So negative, well, so we have parentheses 1, parentheses negative 393.5, okay, parentheses plus 2, parentheses negative 285.8, parentheses right there, and then parentheses again, okay, minus parentheses 1, parentheses negative 74.81, parentheses, and then parentheses again. And what is our answer in the end? We have a negative 90.29. And what's the unit? It's kilojoule over mole. Okay, what does that tell you? The negative tell you it is an exothermic reaction. Isn't that easy? Next, let's solve for delta S, which is standard formation of entropy. So for delta S, the same thing, product minus reactant. So we have 1 mole of carbon dioxide, and we look at the values for delta S formation, which in this case for carbon dioxide is right here. So it's 213.6, and then we have 2 moles of water, 2 right there, right? And water, where is water? Right here, 69.91. And if you haven't noticed so far, all the values for delta S formation of entropy, they are positive, because look at that. We learned that the only perfect condition where the entropy is, or zero disorder, is at 0 Kelvin. And of course, here we're talking about standard, that's 25 degrees Celsius. So of course, all of your delta S will be positive. So keep that in mind. Now let's go back to this. So we close the product side with another bracket, or parenthesis in that case. So minus the reactant side, which in this case, what do we have? 1 moles of CH4, which we know is 186.2, and then also 2 moles of oxygen. Remember, delta S is not the same thing as delta H and delta G. It has some values. So in this case, 2 moles of oxygen, it is 205.138. Now let's plug into the calculator. Notice how the bracket represents parentheses. So just parenthesis there, 1, okay, 213.6, parenthesis plus 2, parenthesis 69.91, parenthesis, and parenthesis again, minus parenthesis 1, parenthesis 186.2, parenthesis plus 2, 205.138, parenthesis, and then parenthesis with a bracket again. And the answer is negative 243.056. And what's the unit? Of course, it is joule over mole time Kelvin. Now let's solve for delta G naught. The same thing, product minus reactant. The same thing, the sum of the product minus the sum of reactant. So in this case, we have the product again, 1 moles of carbon dioxide, and the values for carbon dioxide is negative 394.4. And that's for carbon dioxide. Now we have water, so which is 2 moles, so 2 right there. Time, what's the values for water? Negative 237.2. And then we'll close it up because we are done with the product side. Let's move to the reactant side. We have bracket right there, which in this case, what do we have? We have 1 mole of methane right there. So what's the value for methane? Negative 50.75. Okay. And then we add to oxygen. I know right away it gotta be 0 because it is an element. So, oh, it is 0. So we can just ignore that. Or put a 0 there. Now let's plug everything into a calculator. Remember that bracket represents parentheses. Or if you like to do it the long way, you can simplify them one by one, your choice. But I like to plug them all at once. So parentheses 1, negative 4 plus 2, parentheses negative 237.2, parenthesis, and parenthesis again, minus, parenthesis, 1, negative 50.75, parenthesis. What do we have? And the unit is kilojoule over mole. And what's that negative tell you? That this reaction is spontaneous. It makes sense. Methane is extremely combustible when exposed to oxygen, right? Which releases a lot of energy in terms of delta H. So that's all you have to do to calculate for the delta H, delta S, and delta G naught.